Now, let us talk about aryl diazonium salts. These salts are formed from primary amine when we react the primary amine with nitrous acid and transform it into nitrogen connected to another one and a salt. So this could be stabilized with something like the chloride. The problem with nitrous acid is that it's not stable enough, so usually we can use sodium nitrite in the presence of a strong acid like hydrochloric acid or sulfuric acid, and then we transform it into the salt. Azo means nitrogen, so diazo means we have two nitrogen atoms connected to each other in this case. We can also rewrite this compound as, say, it's going to be similar to nitrogen Cl minus. So whichever way you see it written, you should clearly notice that it's the nitrogen that is attached to the aromatic compound. Because nitrogen is a good leaving group, so therefore it is possible to perform a variety of reactions. And this compound can be stabilized by resonance. That's why the aryl diazonium salts are the ones that have a wide kind of synthetic application compared to the others. So we can be able to transform it into, let's say, fluorobenzene. If we use fluoroboric acid, HBF4, and of course it also requires some heat to kick out the nitrogen gas, and then we end up with the fluorobenzene. Another reaction we could do is to transform it into chlorobenzene. So we can form it into chlorobenzene. We can also be able to transform it into iodobenzene. We can be able to transform it into cyanobenzene, or what is commonly known as the benzonitrile. Now for this transformation, all we need is copper chloride. Here we need copper iodide. Here we need copper attached to the cyano group, that is copper nitrile. Other transformations we could do involve formation of benzene itself. So we install a hydrogen, and this requires the use of hypochlorous acid, so HpO2. We could also transform it into a phenol. If we use water, H2O, together with heat. Another transformation we could do is we could do electrophilic aromatic substitution. For example, let us do it from here. So we can transform this into if we use something like, let's say we use anisole. Now we know that anisole is more activated, the benzene ring is more activated, so it's able to do a nucleophilic attack on an electrophile. So then what could happen is, of course this is going to attach it in the para position, so what could happen is we could have this one going over here to attack that position, and this one goes here. So we end up with a compound that looks like this. 1, 2, 3, 4, 5, 6. And this is attached here. Nitrogen, nitrogen. We no longer have the 4 mole plus charge. This nitrogen is now connected to an aromatic compound. And then we have a 4 mole charge here. In the presence of chloride ion, it will be able to deprotonate, and now the charge goes there, the electrons, and then we form the product, which is going to look like this. The anisole group. Then we have nitrogen connected to nitrogen, which is again connected to the aromatic compound. So we called this electrophilic aromatic substitution. So with the electrophilic aromatic substitution, keep in mind again that in this case, this compound here, it's going to form the sigma complex, which we learned a few weeks ago. So the sigma complex is going to be stable, and then the chloride ion is going to come in to do deprotonation, and then we form plus HCl. So looking at the reactions we have done, you can see how we can be able to use an aniline. We can use an aniline together with nitrous acid, and then we can transform it into aryl diazonium salt. Then we can be able to transform the diazonium salt into a variety of compounds, some of which we never did before. So now we know how we can transform a diazonium salt into fluorobenzene. So we can synthesize fluorobenzene, we can synthesize chlorobenzene, iodobenzene, benzonitrile, benzene itself, phenol, and even other compounds. Now when we do this reaction that involves electrophilic aromatic substitution, we end up doing what is called azocoupling. So this is called azocoupling. And with azocoupling, we can play around with these compounds to generate a dye, that is, compounds with nice colors based on the substituents that are attached to each of the groups here. Thank you for watching.